by looking at what a vector is as against what scalar quantities are, right? So we knew, and I think there were some who may not have known then, that a vector is a quantity that has magnitude, which means it has an amount, but it also depends on a direction. And so for vectors, direction is very important. However, the scalar quantity is only defined by its amount, how much it has, right? And then we talked about vectors that let me look at the new messages. Okay. All right, so we talked about vectors that they can be graphically depicted as a line with an arrow. Now, when we have two lines with arrows in the same direction, but they are not the same size, they are not the same vector. However, if they have the same length as well as they are in the same direction, it doesn't matter which part of space those two lines exist, they are the same vector. Okay, so the picture in figure 1b shows different vectors. Because they are parallel to each other, they are the same vector. Please, madam, we can't hear your voice. You can't hear me. Somebody has sent a message that you can't hear my voice. Okay, let me give you opportunity to respond. All right, so let me know, please. Can you hear me or not?
Yes, please, we can hear you.
Okay.
Madam, we can hear you.
We can hear you.
Okay.
We can hear you clear.
We can hear you.
Okay, then let's continue. So, like we were saying, when vectors exist with the same length or magnitude, so the length that we graphically depict a vector with gives us information on the magnitude, how large, how much the content that vector has. And the direction, if they are also in the same direction, then they are the same vector, regardless of where you find them. So in that sense, if we have a vector here, another vector here, because they are in the same direction and they have the same length, they are the same vector. However, if I have another vector that is moving in this direction, in the opposite direction, though it has the same length as the first vector, it is not the same vector. If anything, it is an opposite of the same vector because it is in the opposite direction. Okay, and so you see that with vectors, the negative sign is of utmost importance. You cannot just ignore it. And most of the time, the negative sign depicts a direction that is opposite the expected direction. Okay. And in our work, we are going to depict a vector by a capital alphabet with an arrow on top of it. Okay, so an alphabet with an arrow on top of it will depict all vectors that we want to describe. But when you go into textbooks, you'll find that sometimes they depict their vectors by making them bold, so thicker than normal size. That's how they depict it. Okay, let's see. So next we talked about the unit vector, right? When we say something is unit, it means that it has a magnitude of 1. Okay, so the unit vector has a magnitude of 1. So it is a vector that has a magnitude of 1 and a direction. And because this vector has a magnitude of 1, we know that when one multiplies anything, it's that same thing. Okay, so anytime we see a lowercase alphabet with a heart on it, we should understand that it is a unit vector. It has a magnitude of 1. And so whatever it is multiplying, it takes the magnitude of that quantity it is multiplying and gives its direction to it. So the unit vector only has a direction. Its magnitude is a unit, meaning 1 magnitude. And so because of that, we can define all vectors in terms of their magnitude and their unit vectors. The unit vector shows that the vector has a direction, okay, that quantity is dependent on its direction. And so if you see us write something like this, then we write A, the magnitude, and then A with a heart like this. This unit vector here is depicting the direction that A has along with its magnitude. Okay, so anytime you see a lowercase alphabet with a heart, it is a unit vector. All right, then we talked about the triangle law of vectors and the fact that for the triangle law of vectors, we understood that when two vectors, right, they form the sides of a certain triangle, there should be a third vector. The third vector is assumed to be the resultant, okay, the resultant of that. So when we resolve the two, so let's say A is moving in this direction, right, then we have a vector B moving in that direction. Let me do them on a different side. So we have like a vector A moving in this direction. We have another vector moving B in that direction. Then the two of them, we can resolve their resultants, but the resultant should move from the source of A to the destination of B. Okay, if that is the case, then it means that the C is the resultant. So vector C is the resultant. A and then B are the vectors in question. Now, what if we have these same vectors? However, let's go to the next page and do that there because there is more space on that next page. Okay, so we also talked about having two vectors. Okay, so we have A in this direction and then we have B in the opposite direction and then we have C moving from A to B. Now, if we know which one is the resultant, and usually we take C to be the resultant. So assuming that this C here is the resultant vector, okay, then A is in this direction and then B is in the opposite direction that we expected it to be. Remember that from the triangle law, they all have to be in the same pattern. So A is moving from left to right. We expect B to also continue from where A ended and then move outward. But here we have B rather falling into where A is. So what we need to do is to check which one is the resultant and then see the direction of the resultant. Now we see here that C, which is the resultant, is moving from the A towards the B, and because in our example the C is a positive vector, it means that B is the one that has changed its direction, or it has a changed direction. Okay, so far as B has the changed direction, it means that B is the negative vector. So all we need to do is to take B. Let me see if I can rotate it. No, I can't. Okay, so what we will do is you take the B and then you rotate it, okay, so that it will be in the proper direction, and then you give B a negative, okay, so that now we will be able to resolve it in the same way that we know using the triangle law of vector addition, right? And so we will have A now plus what? Minus B, okay, being equal to C, which is also a positive. So we always use the resultant vector's direction to determine which vector has a changed direction. So then this then also means that if C were in the opposite direction, if C were to go in this direction, okay, then we know that C, though it is moving in this direction, is inherently positive, right? And then B is also in that same direction, the original direction B was in, right? This then shows that the negative vector is not B, but rather A is the negative vector, because we are taking that cue from the direction of C and as to whether C is positive or negative. Okay, Adopisa, you want to record it on your computer? I think it will. Am I recording? I'm already recording, so let me record it and send it, okay? Because if you're also recording, it's going to take too much network resources resources, and we might end up not having enough network to help us. Okay, so I will decline at this time. All right, so let's continue. Before we go, hey, a long chat, 10 new messages. Go and sit down. You people should check your network. I can hear you loud and clear. Your voice is clear here. Okay. All right, okay. Okay, so next. Scalar multiplication, that's what we talked about. We actually understood it, I hope, but we talked about the fact that the scalar, it doesn't have any direction. However, it's able to give more volume, if anything, I mean, for want of a better word, is able to give more volume to, or more amount or less amount to the vector in question. Now, in this equation here, the vector b is equal to ka. A is the independent vector. B is the dependent vector. B depends on the amount of A times whatever scalar value to get its own magnitude, its new magnitude. So if K is equal to 1, it means that B and A are the same. If K is greater than 1, then it means that B is longer than A, meaning B has a higher magnitude than A. If K is less than 1, which means it is between 0 and 1, so 0.5, 0.8, 1/2, a fraction of 1, then it means that B is smaller than A, right, in terms of magnitude. Then if K is less than 0, all right, so -5, -7, etc., then it means that B is the opposite, is in the opposite direction as A. So this means that if A was going this way, B is moving in that direction. Okay, so it's in the opposite direction as A. And if K is greater than 0, then it means that K, the scalar quantity, is a positive value, and whether it is a higher positive value or just 1, it is in the same direction. B is in the same direction as A, right? So these are a few conclusions and summary we had on this slide. This is for the sake of those who probably could not be in class that day. Okay, then we also talked about another form of multiplication, and this is where we ended, the vector multiplication of called the dot product. We also have the cross product. Now, the dot product produces a scalar quantity, which means that it produces an amount that is only defined by its magnitude. We don't really need its direction of effect, right? It's only completely defined by its magnitude. An example of that is work. Okay, work, the factors of work have what do you call it? Vector quantities. However, when they multiply to give us work, they only give us something that we only need to describe it by its magnitude, right? And that is the reason why work is a scalar quantity. Okay. So the dot product, early on when we met, somebody wanted more explanation on the dot product, and we will, because I promised that our second meeting we were going to discuss or do more examples on what we had done early on, and so we will do more examples. Okay, can you see the whiteboard? Send a message if you can, or you can just raise your hand or send a smiley or something. Hey, you have started annotating. Nah, Gabriel. Okay, you raised your hand. Okay, all right. Okay, so I'll take it that you are not intentionally writing on the pages. When you are raising your hand, that it ends up writing on the page. So I'll just clean it and we all pretend that it never happened. But don't intentionally write on the page, please. Okay. Hey, who is that? Your names show when you write on the page, so stop it. Okay, so now we have a vector A, right? Then it is multiplying another vector by using the dot product. That vector is B. Now we are saying that the outcome of this vector product is A, the magnitude of A. Remember last time we said we are going to depict magnitude by putting the vector inside two bars, okay? Meaning that it's only its magnitude we are interested in. Okay, so the magnitude of A, which means the amount of A times the amount of B. So this here is ordinary multiplication, okay? Then all of these multiplying the cos of the small angle between them. If you recall, we talked about this small angle, and I said that supposing we have a vector, one moment, so we have a vector here, B, okay, and then another vector, A. Now, these two vectors, let's call this B and this one A. They have an angle here, and they also have, let me use a different color. Where are the colors? Okay, and they also have an angle there. Right, so sometimes because we are used to only looking at the small angles, we forget that there is a big angle also behind them. Or if we even put it this way, let's say we have a vector this way and then another vector that way, okay? There is an angle here and another angle there. Right, now from the definition of the dot product, it is the small angle that we are interested in, the smaller angle of the two that we are interested in. So which means that if here is 30 degrees, okay, then it means the bigger angle is what? 330 degrees, because both of them should add up to 360 degrees. And so what the product of A and B will give us will be A's magnitude times B's magnitude, all times cos 30 and not cos 330. Okay, I don't know why they have put collaboration. Robert Quayson, you wrote on the page, okay? So don't do that. You are taking our time. Okay. All right. Okay. So, okay. Now let's go to the second page and then try to look at some examples. So let's say we have y, x. Now at this side, we have, let's say 3, and then over here we have 4. So which means 1, 2, 3. Okay. So 1, 2, 3, then 4. 1, 2, 4, 5, 6. Now let's look at two vectors here. So there is a vector here that ends there, and then there is another vector here. The vectors are hard to take away. Okay, so now what we want to do is to add, let's name the vectors first. Please, madam, we can't see. You can't see, but you keep pushing the board. Richmond, please, the board appeared to be, yeah, somebody just zoomed it out. Zoom has made their whiteboard collaborative, so it's like you are not the only one who can write on it. Let's move from Zoom and let's use Microsoft Whiteboard. I'm going to close the Zoom whiteboard and then we will use Microsoft Whiteboard because I don't like the fact that they are just... So I'll go back to sharing the lecture notes. And then let me find Microsoft Whiteboard. At least on that, you cannot be writing, and then you'll be able to see the screen well. 22 new messages. Appears to be zoomed out. Oh, it's very small. Madam, the board is small. Madam, please. Okay. All right. Let's use Microsoft Whiteboard, okay? And then I will go on to that again, what we started. Let me share that. Okay. So now we are using Microsoft Whiteboard. Slow or no internet. Oh, but you guys are still here, so I'm able to see changes. Okay. All right. So I hope you can see it now. Okay. Let me know if you can see the whiteboard. Yes, ma'am. Okay. Okay. All right. So, hey, this is really thick. Maybe too thick. Let me see. Okay. All right. It seems here I have to just deal with this like that. So let's go. So we have the x-axis and then the y-axis, okay? Then on this axis, we have 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, right? So we are going to put in two vectors. So 1 is in this direction. Let's call this vector B. Then the other is, let's give it a different color. So vector A. Right. And now we are to find A plus B. Okay, A plus B. Now, if you recall, we have said that it doesn't matter where a vector is in space. Okay, if it is in a certain direction with a certain length, then it can be anywhere and it is still the same vector. So let me see if I can move this vector. It seems I can't move it. Let me try and see. Okay, so now because of what we want to add them first, let's see what vector A is and what vector B also is. Okay, so when we extend, A is somewhere around 3.2 on the x-axis and 1 on the y-axis. Okay, but it starts from 1. Please, let's see that. It starts from 1. So which means that it is actually around 2.2. So the 3 will go away. Then we will write 2.2 because it starts from 1. And then on the y-axis, it starts from 0 to 1. So that is A. Now B starts from 4 and ends somewhere between 6 and 7 on the x-axis. Then on the y-axis, let's say it's around 4. Okay, so we have about 6.8 on the x-axis. Sorry, I'm making the mistake again. It starts from 4. Okay, and so 4 to 6.8, that will be 2.8 on the x-axis, and then from 0 to 4 on the y-axis, and then so which means 4 on the y-axis. Right. So now we need to find A plus B. How do we do that? We can move any of them to any point because remember what we said. So far as it is the same vector, it doesn't matter where it is in space. So let's move B and then put B at the top side of A. Okay. Then at that point, we can say that C should comfortably start from A and end at B. So how will we resolve the C? How will we resolve the C? Now we know that A has a certain length and it makes a certain angle with the x-axis. Okay, and then B also has a certain length and it also makes a certain angle with the same x-axis. Remember that B was already on the x-axis before we took it and then put it at the top side of A. So B also makes an angle on the x-axis. Let me clean some of them so that the board will not be so messy. But let's just remember, let's write their values somewhere. A was 2.2 at 1 and then B is 2.8 at 4 on the y-axis. Now let's also realize that, let me see if I can move this. Apia, your hand is up. One moment, let me give you the opportunity to talk.
Hello, madam. Madam, please, can you take how you took your points? I don't really understand that part.
What did you say, please?
Please, I don't understand how you took your points.
How I took the points?
Yes, madam.
Oh, okay. All right, Apia. Okay. Let me go over that side again. Okay. Thank you for muting yourself. Okay. I want us to move to a different section on the whiteboard, but this whiteboard is not giving us the opportunity. I'm coming. Okay. So up here, let's go through this together. Okay. Hey, the ruler is like this, so I want it to be straight. Okay. Let's start from here. Oh, okay. I have this. All right. Okay. So up here, sorry, it's not like I am calling you too much or anything, but let's see. So we have 1, 2, 3, 4, 5, okay? And then we have 1, 2, 3, 4. Okay, someone else's hand is up. That's it. Okay, so this is what we did. 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, then B is a point from 2.8. So now we will have to probably start it from 2 because of, all right, let's just make another B. So B is here, right? So now we have a B here. And let's do A2 when we finish. Let me use a different color for the A. Let me put A here. Okay, then we have A, right? So let's assume that A is from 1 to A begins from 1 here and it ends at 3. Okay, A begins from 1 and ends at 3 on the x-axis. Okay, then B begins from 3 and ends somewhere here. So let's say about 4.9, also on the x-axis. Now, we always write, when we are writing vectors, their coordinates or their points, we always write the x-axis first, and then afterwards we do for the y-axis, okay? So the x-axis value for A starts from 1 and ends at 3. So A is 3 minus 1. Okay, that is the length on the x-axis for A. So that becomes 3. And on the y-axis, A starts from 0 and ends here, which is somewhere around 1. Okay, so we write a comma and then we put its corresponding y-axis. You are not seeing top. Clement, you will see top. Why? Take your time and watch. You will see top. Okay, so this is A. Sorry, 2. I made a mistake again. Sorry, okay. A should rather be 2 because it starts from 1 and ends at 3. So A is 3 minus 1, which is 2. And on the y-axis, A starts from 0, see, and ends here. Okay, so the height that A has is 1, from 0 to 1. Okay, so that's how we got the A, its coordinates. Okay, now B's coordinates also has the x side and then the y side. Okay, on the x-axis, B starts from 3 and then it ends at, let's say, 4.9. Okay, per when we extended from the top to the x-axis. So it starts from 3, ends at 4.9. And so the length for B on the x-axis is 1.9. Okay, then on the y-axis, when we extend from B, it goes to somewhere here. And let's call this point 2.8. Okay, so then it means that on the x-axis, B is 1.9 and on the y-axis, B is about 2.8. Okay, so now we have these two vectors, right? Let's add them, but let me know, please, is the understanding there now? The one who asked the question, do you understand it now? And I think at the moment, anyone else can unmute and then ask another question. Stephen, do you understand how we got the coordinates for A and B now?
Please, madam, why are you subtracting the x-axis? Meanwhile, the y-axis, you are not subtracting that, please.
Oh, I am subtracting the y-axis, but it starts from 0. So when you subtract 0 from anything, we all know that is what? Still 0, right? See, the y-axis side, the A starts from here. It's on the x-axis, okay? Now, anyway, when you are done, kindly mute yourself so that I won't have to mute everyone and force you not to unmute yourselves. Now, if you check, okay, on the x-axis, they don't begin on the 0. This is the origin, okay? At this origin, x is 0, y is also 0, right? And on the x-axis, they don't begin at the origin. They don't begin on the y either. They begin at certain points on the x-axis, okay? And because of where they begin, look at where they are beginning. A starts at 1 and ends around 3. So it's only 2. Now recall that we said that because it is a vector, right, we can move it anywhere. See what happens when we try to move A to the origin. You see that now is on 2 when we move A to the origin, okay? So we know that A is 2. Let's try to move B to the origin, to where x is equal to 0. So we try to move B. We see that B is also about that value we gave it. Okay, so because they are not at the origin, that's why we are subtracting. However, when you take them, their position, because they are here, they are beginning at this point, which is traced to 0 on the y-axis, right? Wherever they are, we are subtracting 0 from them. Now, if I rather put the vector here, let's say I rather put the vector up here. In this space, it is not starting from the 0 point of y, and so we would have to trace where it is beginning from and where it is ending in order to know its magnitude on the y-axis. But if it starts at the point where y is equal to 0, then it means wherever we trace it to, when we subtract 0, we still have that value. If it started from here at this on this x-axis, y is equal to 0. Okay, so if it started from here, then certainly it has begun from y is equal to 0. And then when we trace where it ends, we find that, okay, so between the 0 point of y and then where the magnitude ends, that is how much value it has on the y-axis. I don't know whether it's clear. I think you can still unmute yourselves. I haven't forced you to be muted. Is it clear?
So, madam, I think it's something like initial points and final points.
Yes, initial point and final point, exactly.
Yes.
Okay, all right. So now that we have happily resolved it at initial points and final points, let's go on. Okay, so let's name our B, which means that A is equal to 2, 1, and B is equal to 1.9, 2.8. So these are the values. Now remember that for A, this 2, 1 is on the x-axis, and then, sorry, the 2 is on the x-axis, the 1 is on the y-axis, and then B, 1.9 is on the x-axis, 2.8 is on the y-axis. Give me a moment, my laptop is almost off. Let me charge it. Okay, back. It's not charged. Okay. So we were talking about adding A and B, right? Kindly give me your attention at this point, okay? All right, so let me see if we can move these aside or get a new board. Okay, so A was what? 2 and 1, right? And then B... And B was 1.9 and 2.8, right? And now, before we can add A and B, we need to find, remember that A and B are like this. B is here, A is there, right? And early on, we carried the B on top of the A, okay, so that we can add it according to the triangle law of vector addition. So the B will be there and A. We may put them at the origin, whichever. B can also be the one to start, or A. Now, we need to know, we only know the amount A has on the x-axis as well as the y-axis. Then we know the amount B has on the x-axis as well as the y-axis, which are here, x, y, x, y. But we don't really know the actual value of the line, okay? We don't know the actual magnitude of the A or the actual magnitude of the B, and we need to find it, okay? And we know from Pythagoras' theorem that for A, for example, A is like this. It has an amount on the x-axis and then also a value on the y-axis. So remember that we can extend the side of the y-axis here and it is the same vector. So this is the y. It is what? 90 degrees to the x. Okay, this is x-axis, 90 degrees to that. And if it is 90 degrees to the x, then it means that the value of A is resolved using Pythagoras' theorem. We want the actual magnitude of A. So that magnitude of A means that from this end to that end, we have 2. Then from this end to the top end, we have 1 for the y-axis. Okay, and from Pythagoras' theorem, when we have such a right angle triangle, then the sides that are 90 degrees to each other will be squared, and then we find the square root. So in other words, A squared is equal to x squared plus y squared, okay, because it's on its value on the x-axis and its value on the y. And so A will now become the square root of x squared plus y squared, okay? And so we have A being equal to, on the x-axis, what is the value of A on the x-axis? Tell me. I want you to participate so that you understand.
2.
Okay, thank you very much. So 2 squared. Then the value of A on the y-axis.
1.
Okay, thank you. 1 squared. Okay. It's okay. The noise. So this means that A is equal to square root of 4 plus 1, which is then square root of 5. And what is the square root of 5?
2 root 2.
What?
Who said 2 root?
What is the square root of?
2.23.
2.23.
Okay, so 2.23. Okay, so which means that 2.23 is the actual magnitude of A. When we take A like this magnitude here is 2.23. Okay, now we know the magnitude of A. Now let's find the magnitude of B. Right, now let's remember that B is here. We will extend the x-axis and the y-axis to B. Okay, so this is y, and over here we have the x-axis. Okay. The noise, mute yourself, please. Remember to mute yourself so that I will not have to mute everybody. So now let's extend the y here. That's the y-axis we are extending to. Okay, the y-axis we have extended here, right? So y. And remember, they are the same thing if they are in the same direction and the same length. And on the y-axis, let me mute everybody. So on the y-axis, B has a value of 2.8, and then on the x-axis, it has an amount of 1.9. That's why B is equal to 1.9, 2.8. So just like A, B is also a right-angled triangle, okay? 90 degrees here, this side is 2.8. And this end is 1.9. So then it means that B is resolved from the x-axis to where it ends on the y-axis. That is B. So to get the actual magnitude of B, we do the same thing. B squared is equal to x squared plus y squared. And therefore B is equal to root of x squared plus y squared. Okay, this will give us B to be equal to root of 1.9 squared plus 2.8 squared. So kindly do it for me. I will unmute you for you to speak. Okay, so tell us what you had. What did you get for B?
3.38.
Okay. So B is equal to 3.38.
Yes, madam.
My board is misbehaving. I can't find. Okay, 3.38. Okay, let's look for a new whiteboard to continue. So, do you remember the magnitude of A? A was 2.3 something, right?
2.23.
Okay.
2.23.
And then B is 3.38.
Yes, madam.
Okay, so now we have these as the magnitudes of A and B, right? So in other words, on the y and then also on the x-axis, we have A here. I think A was more like this. Then let me just get another. Then B also continuing like this. Okay, now A is 2.23 and B is 3.38. Now we need to find C. So C will start at A and then end at B. Okay, so we have C here, right? And so the value of C is actually where the value that C will have is actually where A and then B ended, okay? Where the values of A and then the value of B ended. On the x-axis, we had A being 2. On the y-axis, it is 1. Then B on the x-axis is 1.9. And on the y-axis, B is what? 2.8. That is our original values, okay? So C, because B is now added to A, right on top of A, C is going to be the A's x-axis plus B's x-axis. That's on the x. Then A's y-axis plus B's y-axis, okay? So C will be 2 plus 1.9 and the y-axis 1 plus 2.8 on the y. So C becomes 3.9 at 3.9 and at 3.8. So where C has reached here, right, is at a point called 3.9 on the x-axis and 3.8 on the y-axis. Okay, but the actual value of C can only be determined by extending, this is the y, and then C's extension towards the x-axis, okay? And we see that these two are 90 degrees. So C now has a larger 90-degree triangle. And so for C, we have 3.9 here and 3.8 there. The actual magnitude of C is equal to C's value on the x-axis. C squared is equal to X's value on the x-axis plus Its value on the y-axis. Okay, and that is 3.9 squared plus 3.8 squared. So to find C, we have to find the square root of both of them. And that will be, what is what?
5.44.
5.44. So the magnitude, yeah, thank you very much. So the magnitude of B is 5.45. 45.
Madam is 4.5.
Okay.
5.45.
5.4.
So 5.45. Let's put that to here. Right. So this is the magnitude of B. And these are the coordinates of B. Okay. So the values on the X and Y axis, the magnitude of C, the magnitude of C and the coordinates of C. That's C's values on the X and C's value on the Y axis. Okay. All right. So I would have said let's continue next week, but let's now go and let's now find the angles, because remember that A is making an angle on the X to the x-axis. B is also doing same. Let's put A here, B there. B is also doing same. When we extend the x-axis up to B, B is also making an angle on the x-axis. Let me take another extension for that. Okay, and remember that we can extend this because so far as it is parallel, it is the same vector. Okay, so when we extend the x-axis towards where the B is, we see that B has an angle that it makes on the x-axis, and then C also has an angle that it also makes on the x-axis, right? So now let's see how we find these angles. Okay, let me see if I can move all these far so that we use the same page. Okay, so to find the angles, we are going to employ tan theta. Tan theta is equal to what? Opposite over adjacent, right? The opposite angle over the adjacent angle. That is tan theta. Okay. Now what we are trying to find, the value we are trying to find, for that we know that opposite here for each of the angles, okay, the line that is opposite the angles are the y-axis, and the line that is adjacent to the angle, that is the line that the angle cuts apart from the hypotenuse, that line is the x-axis. Okay, so this means that tan theta is equal to y over x all the time. Okay, y over x. So for A, its x is 2 and its y is 1. B, its x is 1.9 and its y is 2.8. Then C, its x is 3.9 and the y is 3.8. Okay, so for the angle of A, its angle, that will be equal to, we find that with tan theta is equal to y over x, so 1 over 2. And therefore, the angle theta is equal to tan inverse of 1 over 2. And what is that? Oh, I have muted you.
26.56.
It's what?
26.56.
26.56. Okay. Degrees.
0.46 degrees.
0.1.
No.
Please make sure your calculator is set to degrees and not gradient or radian.
Please don't
Okay.
confuse yourselves.
That means 26.5.
26.56.
Yeah.
Okay, now let me also do it and see. Yeah,
Yes, madam, do it and see.
26.565. That
Yes,
is right. If your calculator is set to radians, it will give you a different value. Okay, so it means that the angle of A is equal to 26.565 degrees. Now let's check the angle of B. So that's one. Oh, let me use theta, then B down. Will be what? Tan theta is equal to, which one is y?
2.8.
Thank you. And the x?
1.9.
1.9. So then the angle for B is
1.9.
tan inverse of 2.8 over 1.9. And what is that?
Those,
Around
55.84.
55.84.
Okay.
55.84.
Is it 55 or 65?
55.
55.84.
Okay. Thank you very much.
Welcome, madam.
So that is the angle for B. So now what I want you to do is find the angle for C. Okay, find the angle for C.
44.26.
Is what?
44.26.
Okay, so he had, are you sure C is supposed to be bigger than that?
44.26.
Oh, you also had the same. Okay,
Yes.
so
Yes,
that is 44.26 degrees. Right. Okay. So that's for today. We have been recording the lecture, and so when it is done, I will put it on YouTube, and then I'll send the link to you so that anyone who was not part of the class or could not hear anything at a certain point can go back
Okay, madam.
and then check. All right. So once that's done, I think we are done for the day.
Question.
Yes, a question. Yes.
The resultant values. Instead of going through the A value and then B value, before going to that values to get the resultant of each other. No? I insist that we have find the magnitude of A and B, which is 3.28 and then 2.23. Madam, please, can you use this value to find the C?
You can use these values to find C after you have found their angles.
Okay.
Because you need to get the angles before you can use these values to find C.
Okay.
Okay, because they do not add immediately, like just adding to get C.
Okay. And the magnitude.
Which ones? The magnitudes of
there is no unit or the.
Oh no, unless you